Hi, everyone. So I think we're live now. Um, Thank you to the Hydrogen Business Council for having me today. My name is Ivette Vera-Perez, and I am the National Team Lead for Account Management at MITACS. I also serve on the board of the Ontario Clean Technologies Industry Association, OCTIA. And I'll be happy to talk to you later about MITACS or OCTIA and how we can help you. In our panel today, we have four top Ontario researchers in the hydrogen space. We will have Professor Micheal Fowler, Professor Xio Wu, Roydon Fraser, and Professor Paul O'Brien. The first three professors are from University of Waterloo, and Professor O'Brien is from York University. Next slide, please. Thanks. So as an introduction to today's panel on the topic of university research and development to support hydrogen deployment, I'd like to start by referencing this study from 2018 that outlined the talent involved in the hydrogen and fuel cell research spaces in Canada. So as we see, the bulk of the academic research is conducted by postgraduate students, international or Canadian, who are mentored and supervised by academic researchers, such as our panelists today. I am proud to say that MITACS supports a high number of these students through our programs. Next slide, Duncan, please. Thanks. I won't go into details about MITACS programs, but what I will say is that we are a national non-for-profit organization with the mandate to foster growth and innovation in Canada. So we support companies, we do this by supporting companies in the research and innovation space and basically meet their needs by bringing talent from academia into their own businesses. So whichever operations these companies are developing, new technologies, optimization, improvement of operations, we help them by bringing talent from academia into their own businesses. These are talents this is talent in the form of interns or researchers, students pursuing their masters, their PhDs, college, also postdocs. So highly qualified individuals who would be in a position to help industry move the needle in the right direction in terms of where they're going, in terms of innovation, research and development, and technology development in general. Next slide, please. So MITACS has supported since 2015 650 projects in the hydrogen space. The picture doesn't show very well, but this is just some of the examples, and many of these projects have taken place with the professors today on the panel, which is really cool. So final slide. So that's it for me. Like I said, I would be happy to discuss later on how MITACS can help advance the hydrogen economy in Canada by supporting research and our researchers and our top talent. So having completed this short introduction, I would like to introduce today's panelists. The first panelist today will be Professor Micheal Fowler. Dr. Fowler is a professor in the Department of Chemical Engineering at the University of Waterloo, and he is a Canada Research Chair in Zero Emissions for Vehicles and Hydrogen Energy Systems. Dr. Fowler's primary research interests are in the design and performance of fuel cell stacks and systems, including the modeling of fuel cell system reliability, and research into potential failure modes and causes experiencing fuel cell stacks and battery packs. His research has been extending to include the assessment of electrochemical power sources in vehicles towards adaptive control systems for fuel cells, fuel cell battery, and hybrid systems. This includes the design of facilities for the production and distribution of hydrogen as an energy vector, and including power-to-gas applications for pathways to hydrogen. Welcome, Professor Fowler, and you can start with your presentation today. Thank you.
Okay, we're having issues with my video, but people see that presentation now, the ideas for hydrogen economy?
Yes, we do.
You can see that. Okay, so what I'm looking for, everybody, I'm going to go back to my heading here. I just want to have my email there, and if people have any ideas about the hydrogen economy, we are trying to produce a report, and we are looking for ideas, and we want discussions from all the people in the workshop at the same time. So I'm going to try to look at what you should be able to see now, a slide that says ideas for hydrogen economy right now.
Yes, we do. We don't see the presentation screen, but if you would like to proceed like this, is fine.
That's fine. As long as you can see, the slides, that'll be talk. I'm not that pretty, anyways. All right. So I'm good. What I'm looking for is ideas for the hydrogen economy. The problem that we're going to have is that nobody is going to buy cars, or nobody's going to have Class 8 vehicles if they don't have infrastructure where they can have the infrastructure along the locations or something built. I'm going to go down what I consider the 5 or 9 ideas that we can have and get us started on the hydrogen economy. Note that what I've tried to have is what I call a measured decision. And the measured decision is to keep it low so that it's low cost on the economy impact, so it doesn't have a huge impact in high cost, but what we actually need to get started on there. Do people see a slide next slide now with a little highway there? Hello?
Yes, you
Yes, we
do.
do. Thank you. Yes,
You
yes,
see
we
the
do.
next one? Okay. Okay, so what I've done is all the ideas that I have, I've done some journal papers and they're out there, and if people want a copy of any of the journal papers associated with this, they've been written. I've been written over probably the last 15 years with over about 60 journal papers that have been on hydrogen economy and trying to have it in different locations. What we're looking at right now is we're looking at this slide along the corridor, what I'm calling the hydro corridor along there. If we're going to have Class 8 vehicles, having the infrastructure along those locations, and it makes sense to go to the en route locations, because those locations, they have long-term contracts. There's actually a gas station that is being there. Canadian Tire actually has the contract for, I don't know for how long, but they have that. But we have 9 locations along there. Now, you'll also see what I'm trying to do in the actual journal paper, which I'm looking at this, is I sort of a little gived up on doing the CO2 in this area. What we're doing is we're saying if we have zero emissions vehicles, then we will be improving the corridors with the health impacts. The health impacts themselves will help with CO2, but it will be more impacts on the health impacts. So if I look at the scenarios, and hopefully you see 5 scenarios now.
Yes, we do. Yeah.
Okay. So what the scenarios is 1% of the total number of vehicles, going up to, let's say, just 1% of the vehicles of the Class 8 vehicles. And I'll just say class vehicles, although I'm including Class 7, 8, 9, and 10 vehicles, which are all different, slightly bigger or smaller vehicles. But Class 8 is the most common ones that we have. If we look at these up to about 1% of the share, we've looked at those scenarios. We've said that about 1% of the hydrogen, or about 200 Class 8 vehicles of the total 20,000 truss vehicles of truck or trips that I'm saying. So I'm not really counting the number of trucks. I'm counting the number of trips. I say you have about 500 kilometers per day. So that's about 500. I can see and envision maybe 200 vehicle trips over there and needing hydrogen along the corridor. That's where I see the first change that we can have. The first thing we can say that if we want to see, if you see scenario number 5 here, 1%, then we will need 6 locations of en routes, and the other locations can be moving trucks with hydrogen into them to refuel at the all the other en route stations. So that's what they're worming around us. So what I'm really looking at is I'm looking over the idea of what I call hydrogen economy, is one of the power to gas energy concepts that you'd have. All the common pathways to power to gas is the hydrogen. You go into the grid and you go into the electrolyzer. This is the first thing that we can look at, and it's the more global issue that we have in Ontario. We have a problem with the curtailment of the electricity, and it's coming from both from the nuclear and from the wind. There's a lot of electricity that is curtailed at this time. And that is the challenge that we have. We have all this electricity, and it's calling something. If you look at your bill on your electricity and you see something called global adjustment, we're generating the electricity, but then we're dumping it into the water, or we're dumping it in, or turning off the wind out there. So the first thing we want to do is we want to try to suck up all of that energy, and we may as well, we're paying for that energy anyways, so we may make sense to start to making the energy of the hydrogen anyway, since we're paying for it. So the next thing we say, it should have number third, the 3-1, well, looking at the power to gas, the renewable to the what I call the petroleum option. This is one of the we can have, is that we have lots of cars on the vehicle, and we're going to have those cars on the for the next 10 years for sure. We're going to have lots of cars and lots of trucks there, and we have refineries. They make diesel and they make gasoline. Well, those need hydrogen in those refineries, and we can convert them. Right now we're making them with natural gas, but we can also make some of the electrolyzers can be put into the industrial vehicles. So if you look it over, if you were to install over about 100, which is a lot of them, but if you put in all 100 electrolyzers there and hooked up all the extra electricity we'd have, that would be the equivalent of 30,000 vehicles without changing the type of vehicles, because your gasoline would be getting cleaner on the refinery. It would be getting cleaner on the diesel. And then we would have 30,000 vehicles, because they've been made up the refinery to make the cleaner there. So we're looking at something like that. So I'm going to power for what I'm calling power to gas, the natural there. And if you look at this power to gas one, you see the red line that's coming around here. Yes, we very recently we had a regulation where Enbridge had an approval that said that they can approve up to 2% of the hydrogen in their power to gas. And that's just if you make hydrogen and you just put it into the pipeline right now, then you would have cleaner, because you would have the hydrogen in the natural gas, because it would be using to all the natural gas end users, all the heat they have, all the homes, all the industrial places. There's with your natural gas in here. Now you'll see I put up on title that says 2% regulation, and when it is 2050. I don't envision us achieving the 2050 of zero emissions. Yes, it would be a target, nice to get there, but I doubt we'll there. The natural gas is a really good, clean, low cost gas, and we're still doing it. We're building a new pipeline. We're having liquid to natural gas. We're moving that around the world. Everybody's using natural gas around the world. So yes, everybody would like to go to natural gas, zero emissions, but I can envision probably using natural gas for way there or there. But we could have a transition putting into hydrogen at 2% of the regulation. But you see there, the one under there, I said it'll be never reach the 0.10% of the hydrogen, because they have so much natural gas moving around. You would have to install about 1,000 hydrogen electrolyzers just to get that to the 0.2% if you move it all around the pipeline. So there's other ways that we can look at that. So what we really want to do is start using up the curtailment and stop using the loss of that energy, that cost. The next idea that we had in moving into the economy microgrids, yes, you can have microgrids that can be refueling at the locations, but these are people who are using forklifts. They could eventually get into the train. Would be really nice to go on the Pearson line is an ideal one to be using, starting with it would be train for the natural using hydrogen along the Pearson line. We could use that as a starting point. But we could use these microgrids. We've already done, they've done them. Walmart has tried one in Calgary. They've also done some modeling of some other locations that people have installed. Canadian Tire has the distribution centers. These are, the economies can be installed. They could be installed with a small amount of electricity or a lot amount of the amount on the economy, because they should be paying for their own microgrids, that they can get to do those right away. The next ideas that we have there in looking for the microgrid, we can be moving that power to mass. We can use the energy arbitrage, and we could have different charge, and we could shift it at locations where they have storage of their hydrogen generations and putting it into their tanks, and they could go back towards those. So this is my time that's coming up right now here. You should be seeing right now the ideas for the hydrogen economy. It says 2020 now. I actually had these ideas for the hydrogen economy for about 6 years ago, but right now we could get the hydrogen refueling on the hydro corridor on route locations right away. That's where we need to get started so that people can start moving Class 8 vehicles along there. Then we can go to power to gas. Then we could go electrolysis for the refineries, or we can go into the pipelines, number 2. Then number 4, the idea there, I have hydrogen, hydrogen enriched in natural gas. We can put some in the pipeline, and we keep installing the electrolyzers everywhere, and then we'll stop you when you hit 2%, but you'll never get the 2% there, because if you start to make the hydrogen, people will start to put them as per fuel cells in the vehicles and the cars eventually. So then you'll be using it there. Also, you can have the microgrids, and you can have the forklifts and the light vehicles there very early. But in 2030, yes, you can say about 2.5% of the fuel vehicles. The presentation by Cummins was saying that they were going to have some vehicles coming out in class vehicles for 2%. Their target is 2.5% for Cummins. So yes, that would be good. I'm not really keen on conversion of the Class 8, but those are ideas. We can do rail cars and locomotives and the Pearson lines. That would suck up a lot of hydrogen. Or you'll hear some other presentations that'll talk about products or season.
Thank you, Professor Fowler.
Okay.
Thank you very much. Everyone, I'll try to move us along a little bit quicker. I might be a little bit shorter with the introductions. Our second panelist today is Professor Xio Wu. Dr. Wu is an assistant professor at the Department of Mechanical and Mechatronics Engineering at the University of Waterloo. He comes with a PhD from MIT, and his research group, the Greener Production at Waterloo, combines expertise in thermal science, material engineering, and techno-economics to develop sustainable technologies. Welcome, Professor Wu.
Thank you, Ivette, for the kind introduction. Good morning, everyone. My name is Xio Wu. I'm an assistant professor at the University of Waterloo. In Professor Fowler's talk, he introduced the 9 ideas for the hydrogen economic in Ontario. Some of these are low-hanging fruits, and you will be very likely to see much progress immediately. Actually, others require us to jump a little bit to reach, but they might be more delicious depending on your taste. So now I'm going to talk about one of these items that shows great potential but requires further R&D, and that is converting green hydrogen and the captured CO2 into higher value products. If we look at the next slide, we'll see the currently hydrogen markets and the projection to 2050. So next slide, please. Yes, so currently you can see that half of the hydrogen is used in ammonia production, which will be further converted into fertilizer. But if you look at the figure on the right, we can look at the projection by the Hydrogen Council. You can see that there are many other new opportunities for hydrogen applications. And I learned from Daryl Wilson's talk yesterday that the Hydrogen Council is a CEO-led organization. So I think you can trust these projections. So you can see from here that the hydrogen will not only have great presence in transportation and power sector, it may also offer new opportunities and potential as feedstocks for carbon capture and utilization, which is so as CCU here. So next slide, we'll see why it's important to develop these ideas to convert hydrogen and CO2 into higher value products. Here you can see an ecosystem which consists of renewable electricity, hydrogen applications, and carbon capture. These 3 areas are all interconnected and will grow with each other. It will also allow us to make the best out of the new infrastructures that we are investing, such as the wind farms, solar PV for the renewable electricity, electrolyzers, hydrogen storage for the hydrogen economic, and also the CO2 capture facilities and CO2 storage for the carbon capture to have a net zero emission in 2050. So now I will show you 3 examples that we are investigating in Waterloo on these topics. The first example is shown on the next slide. It is about converting green hydrogen and captured CO2 into natural gas. This is also called power to gas, which you have learned in Professor Fowler's talk. It can be an energy storage solution for the off-peak renewable electricities, and it can also be a carbon capture, a carbon reduction technology that recycles the CO2 from natural gas combustion. Power to gas is actually not a new technology, and you might have read the news that Germany and some other European countries have already constructed several plants for power to gas. However, its efficiency is still low. And this low efficiency is one of the drawbacks when people are comparing hydrogen with battery technology. So here we were developing a new idea that can combine electrolysis and methanation into one reactor, which you can see here as the root 3. In the conventional reactor, which is shown here in root 1 on the left, it separates the electrolyzer and the methane conversion into 2 reactors. However, if we can combine them into one unit, you can make use of the thermal and chemical integration, and also you can improve the process efficiency. We did some analysis, which is shown on the right. You can see the blue and red lines with diamond symbols, which shows the efficiency of this new root 3, which is higher than the broken lines, which are for the separated case. So combining these 2 reactors into one unit, we not only increase the efficiency, but we can decrease the footprint or the space that is required to house this reactor. However, how to integrate them together in a more efficient way and how to manufacture these complex reactors are still needed some R&D and needs our efforts. The next slide shows the second example, that is converting green hydrogen and captured CO2 into drop-in aviation and marine fuels. You can see from the schematic that there are 3 different subsystems. We have water electrolysis that produce hydrogen, and then the hydrogen reduce the CO2 into CO for downstream chemical reactors. Actually, some researchers develop new processes that can directly use CO2 as a feedstock, and that means that the reducer might not be required later. And we also have on the right that the catalytic reactor to produce long-chain alkane or methanols for the fuels. So these different reactors, they work at different scales. We have chemical processes, the catalytic reactions usually favors large-scale production, but the electrolyzers and the reducers can be modularized, which have a smaller space and smaller footprint. And they also run at different times. So we learned that electrolyzer usually uses the off-peak electricity to be more economic. So it can be on-off operations. However, the chemical reactors favors working 24/7 because we want to maximize the production. And in order to integrate this different process of different scales in space and in time, more R&D is needed to improve the flexibility of the process as well as the efficiency. So the goal is to decrease the cost. And the third example is on the next slide, where we showed green ammonia production. So here we don't have CO2 as a feedstock, but we would decrease CO2 emission in the fertilizer production process. So in the group, we utilize plasma-assisted catalysis so that we can convert ammonia from air and water directly from electricity. This will also favor small-scale production. So on the right figure, you can see that the levelized cost of ammonia production use different approaches. Haber-Bosch process, the HBP shown here, is the conventional large-scale ammonia production, and the cost is around $500 and $600 per ton ammonia produced. However, if you want to scale it down for distributed production, the cost increases sharply because it's difficult to scale down the reactor as well as the air separation unit that is required to separate nitrogen and oxygen. However, when we have this type of plasma electrochemical cell, which is PEC on the plot, the cost for this small scale production is much lower than the HBP. And also, if the electricity price drops, this electrochemical process will be more competitive. And in this case, more R&D is needed to understand the mechanism for plasma catalysis, how we can incorporate plasma and catalytic reactions into one reactor so that we can control it better and we can decrease the final energy consumption. To conclude, on the next slide, we see the formation of this new ecosystem, and each of these components will need to grow together to thrive. So the goal is not about cultivating only one of these components, for example, hydrogen economic, but to see how we can make the best use of them all to improve the sustainability of our industry and our life. So sustainable development is our ultimate goal for our efforts. Thank you so much.
Thank you very much, Professor Wu. Our next panelist is Professor Roydon Fraser from the University of Waterloo. Dr. Fraser is a professor in the Mechanical and Mechatronics Engineering Department as well. He's also the department's teaching chair for this group. His primary research interests are hybrid and alternative fuel vehicles, connected automated vehicles, compressed air energy storage, vehicle emissions, and their impact. Welcome, Professor Fraser.
Well, good morning. Thank you very much. I'll try to move this along. First off, my talk is not going to be about my expertise, which is in the area of vehicle design, integration, testing, alternative fuel vehicles. I will be presenting some other research related to this and also related to hydrogen. We have designed and built the first university-built, to our best of our knowledge, fuel cell vehicle that was roadworthy, and it drove between New Jersey, New York, and Washington in the past. So I have lots of hydrogen experience that way. Next slide. We're going to be looking at distributed storage and health benefits of hydrogen. So what is hydrogen's Achilles heel? And it's also the Achilles heel of wind and solar energy. Next slide. Large economical storage, right? And large doesn't mean it's an individual site large. It means having storage in lots of places potentially distributed. Next slide. So if we take a look at hydrogen storage, there's only really two methods. One is tanks, and the other is material-based. So one is physical-based and one is material-based. But I'm going to break the physical-based up into tanks, and at the bottom you'll see there depleted gas wells and co-storage with natural gas, power to gas. So tanks, you can compress it, you can cryo-compress it, which just means you cool it when you compress it, and then you can go all the way to liquid hydrogen. With material-based, you can use an absorbent approach, an organic chemical, a pure chemical that just bounds a lot of hydrogen, or hydrides of different types. Those are the classic, these are the methods that we know about. I'm breaking out the physical into additionally this depleted gas wells and co-storage with natural gas, power to gas, something that Professor Fowler is an expert on. Next slide. And now possibly I'm going to discuss some research that I'm currently involved in very quickly. I work in the area of energy systems. One of those energy systems is compressed air energy storage. And this is an example of one of our ideas for involving hydrogen and compressed air energy storage. Now this is a classic diabatic compressed air energy storage. We have the compressed air on the right going into turbines. You have to provide heat. That heat is provided by combustion, typically natural gas, but it could be hydrogen. That hydrogen could be stored in caverns or depleted wells. It goes along with these compressed air energy systems, and that hydrogen could be part of power to gas and combined with methane, and that provide the thermal energy necessary for these systems to run. These systems can be very large scale. We're talking providing gigawatts of energy for a couple hours a day, if would be not unreasonable for a compressed air energy storage system and system combined with hydrogen. Very large. This would be your utility scale system. This is not exactly what I want to focus on hydrogen wise, because I think some of the ideas that Professor Fowler brought up about a hydrogen highway, and you're going to get things integrated, not big scale initially, it's by small stepping stones. So next slide. So another idea that we're investigating is compressed air energy storage in wells. And these wells, okay, next slide. I'm just emphasizing the part here of this particular diagram is where we've placed this large cavern, usually a salt cavern, with wells. So we actually mechanically drill these wells up to maybe 500 meters, up to maybe 1.5 kilometers, up to maybe 30 inches in diameter. Next slide. So a rough calculation for one of these well bores at 1.5 kilometers depth and 6,000 PSI, and we can go up to 7,500 PSI easily in well bores. They're extremely safe in the sense that, unlike surface tanks, if they explode vertically, so they have a very known explosion direction, and they have the reinforcement of the ground for the rest of their holding of the pressure. So estimates are that one of these deep well bores with this pressure could probably run, and this is based on our fuel cell cars that we've looked at, about 400 to 500 fuel cell cars, about 600 kilometers each for one of these bores. And of course, you could have multiple bores. Next slide, please. And so I summarize things here on this slide. There's a lot of information. Given time, I'm not going to step through it all. I will just point out a couple of things. Storage temperature can go up to 200 degrees. We're talking 50 megapascals and up to 1.5 kilometers depth, probably a minimum of 500 meters depth for one of these systems. What I would like to highlight and for you to pay attention to with all this information is the items in orange. You can store up to 10 plus megawatt hours with the wells. They have a long life. Wells are known to have a long life. It's just inherent in the experience that we have with them. They're independent. This is key. They're independent of geological and geographical conditions. So if you do want to have a distributed hydrogen system along the 401 for, say, a hydrogen highway, this is an ideal solution for storage, we believe, but it still requires research. And it's scalable. You can drill 1 borehole, 2, 3, 4, as many as you need for the size of storage you need in the location you're looking at. And it has a small surface area impact and a large, because it's mainly underground. Next slide, please. So that was a discussion of storage. I know I went very fast there, but I just wanted to plant the idea. The second thing I'm talking about is the other area of, it's a personal and global reasons to invest in hydrogen. So next slide. And that has to do with the health as measured by premature death. And we look at that from emissions from mobile emissions, myself vehicles, and climate change. Next slide. So this is some work by Rebecca Sari, one of my colleagues in Southern Ontario, just looking at the emissions from fleet trucks. So this is a freight truck. So only freight trucks running on the 401, not all trucks. So it's a very limited number, and only looking at the particle 2.5 micron particles, of which, by the way, when you have particle emissions from diesel, over 90% are less than 1 micron in size. And for your information, if you're not aware, the big problem here is the particles of this size, the 2.5 microns and smaller, once you inhale them, they never leave your lungs. They're stuck in there forever. And they also form catalytic sites for some reactions that may not be, maybe damaging to your lungs. So results in premature deaths, in particular, costs were placed on this in this particular study done by Rebecca. And you'll see there to just look at the Toronto area in the dark blue, the estimated damage to the US. So this is actually downstream. This is the emissions in Ontario being carried into the eastern US. This is not even counting the damage to health in Ontario. And we get health damage from Detroit and from Michigan flowing into us. Estimated to be in the millions of dollars, hundreds of millions of dollars here. All right. So there's a lot of economic reasons for looking for something cleaner than diesel fuels. 5% adoption of fuel cells, of hydrogen powered vehicles, doesn't have to be fuel cells, but hydrogen powered vehicles would have a significant impact. In order of 10% would probably meet the Ontario's expectation for reduction in fleet emissions. Next slide. So multi-billion-dollar annual economic damages in Ontario, although that slide was just showing the effects on the US. There's an economic incentive when you take a look at this. Now, this is both death and climate change impacts. The estimate is about $80K per truck you would invest in that if you wanted to do an offset here of the emissions. That's a huge investment if governments were to take that seriously to want to deal with these impacts. And also, like I mentioned, it could meet the Ontario's greenhouse gas reduction targets with a modest change. Next slide. So there's potential hydrogen investment incentives here if there's a political will for it. Next slide. By the way, there's more emissions of concern from cars. We know about NOx and smog production. There's unburned hydrocarbons, carbon dioxide, of course, greenhouse gas, and CO, although it's short term, can be a problem for those with strained respiratory systems in the short term. Diesel trucks add some significant other items, SOx, NH3, and particulate matter. And then there's also about 100,000 toxics more. And that's my area of current research in emissions. Those extra toxics, next slide. Those 1,000+ toxics. And this is just an example of some of the toxics: benzene, phenols, aerosols, formaldehydes, toluenes, and the things that they affect: cancer, heart disease, respiratory disease, neurological effects. Mostly people have looked at respiratory effects of emissions and not these other effects. Next slide. Oh, and this is just types of organs get affected. We don't need to go into the details. Bottom line is it affects your health. So here's an example of some research we've done looking at benzene. This is in St. Paul, Minnesota. Why do we do St. Paul? It's one of the few places in North America where there's sufficient monitoring sites to actually match models to data. And you see here a distribution of benzene through the population, the vicinity of a highway. Where you live does have an impact. Time of day has an impact. And that's one of the things we're now investigating. A lot of these studies are integrated over multiple days. We're now looking at hourly type impacts. Even in fact, just to travel to work is the time of day you travel could have a major impact on the health impacts you experience driving on these highways. Next slide. And yet there's pathways that actually haven't been considered. So these are areas of future research and research we're working on. And in particular, the food deposition, vapor transfer, and root uptake, those three methods. There's been some on on deposition on agriculture crops, but the root uptake and the vapor transfer is not well studied, and wildlife and the environment is basically ignored in terms of impact. So again, additional impacts that have yet to be considered in the costs that I was describing earlier. Next slide. And so as a final slide, we'll just run this video, take a look at the exhaust. There'll be a little puff of smoke. And that is why I do not follow close behind diesel vehicles anymore. I do not want to have those particles stuck in the lungs forever, because they will be in my lungs forever. And there's all these toxics in there. And these are good reasons, once people are aware, for moving away from our diesel trucks on the highway towards a hydrogen economy. And next slide is simply the questions. So I will end my talk there and let us move on to the next presenter. Thank you very much.
Thank you, Professor Fraser. That was a very impactful last slide with that video. Our final panelist today is Professor Paul O'Brien. Dr. O'Brien is an assistant professor with the Lassonde School of Engineering at York University. He is the director of the Advanced Materials for Sustainable Energy Technologies Laboratory, and one of his research interests is life cycle of assessment of energy technologies. Welcome, Professor O'Brien.
Titled Hydrogen Production Options, Perspectives Gained from Life Cycle Assessment. We'll first go over some motivation for conducting life cycle assessment on hydrogen production techniques. Then I'll provide a very brief overview of the LCA process with focus on the global warming impact. We'll then take a look at the global warming potential for some hydrogen production methods, and then wrap things up with some conclusions. In 2015, Canada and 194 other countries reached the Paris Agreement to strengthen the effort to limit the global average temperature rise to below 2 degrees Celsius and to pursue efforts to limit the increase to 1.5 degrees Celsius. Then a year later, in 2016, at COP22, Canada submitted its long-term greenhouse gas development strategy to the United Nations Framework Convention on Climate Change. And to do its part, Canada has set targets of reducing greenhouse gas emissions to 30% below 2005 levels by the year 2030 and to 80% below 2005 levels by mid-century, 2050. In 2005, Canada's greenhouse gas emissions were 748 megatons CO2 equivalent, and so under the proposed strategy, Canada must reduce emissions to 149 megatons of CO2 equivalent by 2050. On this slide, I'll briefly go over the life cycle assessment process. The ISO standard 14040 provides the general framework for conducting an LCA study, and as stated in that standard, carrying out an LCA involves 4 steps. The first step is the definition of goal and scope. For the LCA studies we surveyed for this presentation, the general goal was to determine the environmental impacts of hydrogen production. The other stages are inventory analysis, impact assessment, and interpretation. And I'll go over these stages in more detail on the upcoming slides. A generic illustration of a life cycle assessment process is shown in Figure 1. Defining the scope involves setting the system boundaries. In general, the life cycle of a process includes all steps from when the required raw materials were taken from the ground up to the point when all components involved in the system were disposed of. However, it is extremely difficult to track all processes, and LCA practitioners usually select a set of processes within the overall life cycle to consider. This is most often justified because the environmental impact of some parts of the process are insignificant. So, for example, if one was carrying out an LCA for hydrogen production from electrolysis, the emissions caused from manufacturing and disposing the electrolyzer are typically omitted, because almost all emissions come from the hydrogen production process over the 20 or 30 odd year lifespan of the electrolyzer. Another thing to set when defining the scope is the functional unit. For the LCAs reviewed in this presentation, the functional unit has been set to 1 kilogram of hydrogen produced. Just as the name suggests, in the inventory analysis stage, the resources used and emissions for each process in the life cycle are counted. On this slide, the resources used are not shown, but some emissions are shown. So as an example, the carbon dioxide, methane, and nitrous oxide emitted for all processes in the scope of the study, including plant commissioning, recycling, and plant decommissioning, are tabulated. In the impact assessment phase, the results from the inventory analysis are used to quantify the environmental impacts. There are many different environmental impacts that can be considered, including global warming potential, acidification potential, and resource consumption such as water consumption. However, due to time constraints, in this presentation, we're only going to consider how the global warming potential is calculated, and we're also going to skip over the interpretation phase due to time constraints. On this slide, we take a quick look at how the global warming potential is calculated. From the inventory analysis, we get the sum of each greenhouse gas emitted, considering all processes over the life cycle of the hydrogen production process. We then attain the global warming potentials for each greenhouse gas, which are given in grams of CO2 equivalent per kilogram of that greenhouse gas. So as shown in the table, the global warming potential of carbon dioxide is set to 1. And the fact that methane is set to 25 contributes 25 times as much to global warming as 1 kilogram of carbon dioxide does. Some greenhouse gases, such as SF6, are over 22,000 times worse for contributing to global warming than carbon dioxide is on a per kilogram basis. However, due to the abundance of carbon dioxide emissions, it is still the main contributor to global warming. The equation used to determine the global warming potential is given at the bottom of the slide. And in short, the mass of each emission is multiplied by its individual global warming potential, and then the contribution from all emissions are summed. This slide shows the global warming potential for different hydrogen production methods, given in units of kilograms of carbon dioxide equivalent per kilogram of hydrogen produced. It is important to note that the scope, such as the system boundaries, are not necessarily consistent for all studies shown here. So here we're reporting at a higher level overview of the global warming potential results that have been reported in the literature, with the understanding that the details for each study should be taken into consideration if any two results were to be compared directly. Steam methane reforming is the most widely used and mature hydrogen production process. Steam methane reforming with carbon capture and storage, denoted as CCS on this slide, has been reported to be the most viable approach for large-scale hydrogen production because of its relatively low cost, the existing infrastructure, and the capacity to produce large amounts of hydrogen. The reported global warming potential of hydrogen production ranges from about 5 to 18 kilograms of CO2 equivalent per kilogram of hydrogen produced. When carbon capture and storage is integrated with the steam methane reforming process, it has been reported that the global warming potential can be reduced down to 2 kilograms of CO2 equivalent per kilogram of hydrogen produced. Another method for producing hydrogen is coal gasification. Coal gasification can be done underground, and carbon capture can be integrated, as geological sites suitable for carbon sequestration are often in the nearby vicinity of underground coal seams. In the literature, the reported global warming potential for coal gasification ranges from about 11 to 24 kilograms of CO2 equivalent per kilogram of hydrogen. And when carbon capture is integrated into the process, the global warming potential is reduced to less than 1 kilogram of CO2 equivalent per kilogram of hydrogen. Considering the abundant coal reserves in Alberta, which are estimated to be in the range of 2 to 3 trillion tons, underground coal gasification, along with carbon capture and storage, can potentially be an environmentally benign pathway for large-scale H2 production. It has also been reported that biomass gasification to syngas in the presence of steam is a financially viable hydrogen production option. The results reported for global warming potentials for biomass gasification range from negative 0.5 to 4.4 kilograms of CO2 equivalent per kilogram of hydrogen. Negative global warming potentials are possible because biomass is considered to be carbon neutral feedstock. And of course, this is because the carbon used for biomass growth originally was supplied from the air in any case. It's interesting to note that the global warming potentials become substantially negative when carbon capture is integrated into the process. So for example, the green bars show the global warming potential results for hydrogen production are negative 21.8 and negative 15.8 kilograms of CO2 equivalent per kilogram of hydrogen when carbon capture is integrated with entrained flow and fluidized bed biomass gasification. And of course, hydrogen production via water electrolysis is a very important method. And the global warming potential for hydrogen production via water electrolysis using grid electricity, which is shown as the yellow bars, ranges from about 23 to 29 kilograms of CO2 equivalent per kilogram of hydrogen. Now it's important to note that the electricity used here is assumed to be produced from a mix of sources that includes over 60% production from fossil fuel-based sources. It's a US electricity mix in this case. Of course, in Ontario, the global warming potential associated with hydrogen production using grid electricity would be much lower because almost all the electricity is produced using non-fossil fuel-based sources. And the global warming potential results associated with hydrogen production from electrolysis using solar and wind energy are shown as the dark gray and pink bars here. The global warming potential for solar is about 2 kilograms CO2 equivalent per kilogram of H2, and for wind-based electrolysis, global warming potentials of less than 1 kilogram of CO2 equivalent per kilogram of H2 have been reported. Hydrogen production from water electrolysis has some distinct advantages. Firstly, the purity of the hydrogen produced is very high, and additionally, electrolyzers are flexible in that they can work over a wide range of input power, and for this reason, they can be integrated with renewables. As an interesting point, if all the curtailed and surplus electricity in Ontario were used for hydrogen production via electrolysis, then the amount of hydrogen produced could power about a quarter of the heavy-duty trucking in Ontario. Many other hydrogen production methods have been proposed in the literature, one of them being thermochemical cycling. The copper chloride cycle has been studied extensively because it has a low temperature requirement of about 530 Celsius, this being a relatively low temperature requirement compared to other cycling techniques. The global warming potential for the copper chloride cycle has been reported to be 12.3 kilograms of carbon dioxide equivalent per kilogram of hydrogen produced. However, when using heat from nuclear energy sources to drive the copper chloride cycle, the global warming potential can be reduced to less than 1 kilogram of carbon dioxide equivalent per kilogram of hydrogen produced. In conclusion, a variety of different hydrogen production methods have been reviewed. The best hydrogen production method for a given application will depend on the hydrogen sources available and the purity and amount of hydrogen that is required. Life cycle assessment can be conducted to estimate the global warming potential of the various hydrogen production methods. And finally, life cycle assessment can help to plan for an appropriate mix of hydrogen production methods that can push forth the hydrogen economy while complying with Canada's long-term low greenhouse gas development strategy. Thank you for listening to our presentation.
Thank you very much, Professor O'Brien. We have quite a few questions here, and we have about 15 minutes, so let's see how much we accomplish. Otherwise, we'll make sure that we answer questions in writing and later on. So I have one question for Dr. Fowler first. Dr. Fowler, with the announcement by the Minister of Environment at this conference yesterday, and based on your models and experience, what would be the top action that the province should prioritize in this strategy in order to move the sector forward?
3 electrolyzers along the en route stations, because then you would be able to have Class 8 vehicles moving along the 401. And if you put 4 electrolyzers there, like, I don't know how much they'll cost right now, but probably a couple $1 million, $2 million, around $2 million, maybe a little bit more for each location. But there would give us 3 locations around the en route, would start allowing us to have Class 8 vehicles moving onto the 401. And keep in mind, all the manufacturing that comes from Ontario moves right around that about 401, and it moves into the manufacturing, and that's where all the parts go for all the automotive, and all the parts move along the 401. So I would say start with 4 electrolyzers, which is not a huge amount of money for the Ontario, but it's achievable.
Thank you very much, Professor Fowler. I have a couple more questions here, and let's see how far we get along. Professor Wu, this one is for you. And the question is, how is the synthetic aviation fuel from hydrogen and carbon dioxide compared to biojet fuel?
Yeah, so there are lots of efforts that turning biomass into jet fuels or maritime fuel. So compare with the biojet fuels, we have this chemical process that several advantages. So the first one is that the rate, that means how fast that the fuels can be produced. So chemical processes with catalyst can definitely be more fast. So the rate is higher than the bio processes. And the second is the land use. So we know that when we want to have biomass, we need to have farming. We need a lot of farms that can be compete with the food and other type of things that we need to grow on the farm. But in a chemical reactor, we can incorporate this into a smaller footprint so that we can decrease the space that we need to produce the same amount of fuel. And I think the last thing is when we consider the life cycle analysis that's Paul just mentioned. So when we are growing biomass, we may need to use, for example, fertilizer, and that's actually from hydrogen, and we will emit CO2 along the way. So when we're comparing the life cycle analysis of these two routes, I think their chemical process can have the advantages over that. So that's my answer.
Thank you very much, Professor Wu. I have one question now for Professor Paul O'Brien. So how could you please elaborate on what factors contribute to the significant difference between the two thermochemical copper chlorine cycles?
Hi, Ivette. Thank you for the question. Yes. Yeah, the two different cycles, they were both reported in the same paper. I don't have all the details with me now, but basically it's a matter of where the heat comes from. So probably it might be even the similar or the same cycle, but the energy to drive the cycle may have come in the first place, perhaps from an electricity source, or like some of these papers may have used US grid electricity just as an example. I'm not sure if that's what it was, but in the other case, in the second case, if the heat comes from a source such as nuclear, then since nuclear energy is not giving off so many CO2 emissions, then that will create a large difference in the total amount of CO2 emissions given throughout the entire life cycle. It's important to recall that the life cycle includes everything, right from when raw materials are extracted from the ground to build the reactor in the first place. So there's always going to be some CO2 emissions. In some cases, you can have negative emissions, as mentioned in the presentation. But as you can see, using a fossil fuel free source or a source for over the use phase and the production phase is really important, because that's when the majority of CO2 emissions that's when the majority of CO2 is emitted. And so that's the best we could do. All right, thank you.
Thank you very much, Professor O'Brien. I have one question here for Professor Fraser. Professor Fraser, what is included in the social cost of vehicle emissions? You're on mute. Yeah,
okay.
Very good.
Yeah, I don't know who did that. Anyway, yeah, it's a good question. Yeah, I went over the social cost very fast, and it does rank up there with high numbers. The social cost is based upon health impacts, primarily. It looks at deaths primarily. Looks also at the impact on agriculture productivity. It looks at the impact on property damage, say from acid rain and the like. So it incorporates some things. It also doesn't incorporate the damage on the environment from the toxic emissions, but it does include the damage on the environment from the climate change side of things. So there's a cost of about $32 per ton is sort of the going number ton of CO2 is sort of the going number cost for climate change that's put into that social cost. And then I'll just say there's standard numbers out there for people to use in their research.
If I can just offer along the Hydro 401, our estimate that I just had a student finish the paper, and I can give a copy of that. The health benefit would be $1.4 million per year to just put the 3 electrolyzers on the 401. Health impact.
Thank you very much. And yes, of course, sometimes the audience writes a question directly to one professor, but absolutely, everyone feel free to chime in as well. So I have one more for Paul O'Brien. So it says here, is the dependency of the LCA study for different production methods considerable for studies on different locations? Based on the configuration of inventory that should be considered for the energy sources to be coupled with the production methods and may vary based on locations. So that's one question. There's 2 questions, but I think I'm going to leave it at that for now.
Thanks again. That is a great question. And yes, the life cycle emissions do depend heavily on the location. And and as an example I used before, a lot of production processes depend on you may use electricity. So the CO2 emissions associated with the electricity production become very, very important. And that's one of the great benefits that we have here in Ontario is we have one of the cleanest grids in the world because we hardly use any fossil fuels at all. And based on all of our wind, solar, and nuclear production, we can generate hydrogen with very clean, with very low CO2 emissions, compared to most places in, just say the US, for example, where perhaps maybe 60% of the electricity generation is coal-based. Other factors do come into play too. If you're taking, it becomes less important, but if you want to look at another point for location is you had to transport, when you built the reactor, when you built the electrolyzer, whatever it is you're dealing with, you would have had to transport a bunch of goods. So if you had to transport them a long way, then every little step adds a little bit more CO2 emissions. Thank you.
Correct, thanks. There's a quick follow-up, if you wouldn't mind. How can we distinguish, just one sec, I completely missed the question here. And I think we're gonna leave it, okay, no, here it is. How can we distinguish the most important impact categories that should be studied for hydrogen production LCA study? You said, you alluded a little bit, but yeah.
Yeah, that's another great question. And just to highlight, with most of those studies that we reviewed in the literature, actually within the scope, they almost usually ignore, for example, the disposal phase or a lot of stages at the beginning. Since hydrogen production is intensely about producing the hydrogen, most of the energy over the life cycle comes from the production phase. And to notice that, you just carry out the life cycle assessment and you look for the stages where the numbers for the CO2 emissions are the highest.
Mm-hmm.
Thanks.
Thank you very much. I have one question for Professor Fraser here. Why have the indirect emission pathways that affect health been largely ignored to this date?
Yeah, thank you. Yeah, the indirect pathways have been largely ignored because initially the dominant pathways, such as nitric oxide and smog, it dominates. There's no doubt that it dominates the smog impact, and then the particulate matters are the next largest. So there's no doubt about that. So they've been ignored for that reason, and we're just getting into, if you just look at our emission standards for vehicles, it takes time for regulations to catch up to our knowledge of what's happening. We're just starting to put the particulate matter regulations into place over the last few years and the years to come. Although we knew about it for decades, right? It's a matter of relative risk assessment. And there's also a computational and database difficulty.
And if you don't mind, I have a follow-up. So part of your research is also focusing on on health effects and NOx and others. So from your perspective, which pollutant is responsible for the largest fraction of human health impact, both from gasoline car emissions and from truck diesel emissions?
Yeah, thanks for that question. I think I just answered it, but just to repeat it again.
Yeah, sorry.
The nitric, that's okay. The nitric oxides are, in terms of the emissions, have the largest health impact directly, and that's through the smog, and that's why we have smog indexes or air quality indexes.
Okay. Okay. So one more for Professor O'Brien, if you don't mind. You alluded to this, but what hydrogen production methods are recommended based on life cycle assessment results presented today by you? You made a little bit of a reference, but if you wouldn't mind expanding.
Sure. Thanks again, Ivette, for another good question. So which productions are most important? Well, I think a lot of people have alluded yesterday to the importance of a diverse portfolio of production methods. Basically, when you're trying to decide which, say, hydrogen production method to invest in, you kind of look at what sources of hydrogen you have available. So whether it comes from water or fossil fuels or perhaps underground coal gasification or whatnot. And then you also have to look at the cost is going to come into play. And of course, the end use of the hydrogen. So when you're done producing the hydrogen, you have to take a look at what purity of hydrogen you need and so on. And as mentioned from a lot of these talks today, there's a need for, it's the hydrogen economy. So we need hydrogen in the gas pipelines. We need hydrogen in the vehicles. We need hydrogen everywhere. So it's the diverse demand for hydrogen. So we need a diverse portfolio of production methods to meet that demand in terms of capacity and purity and so on.
Okay.
Thanks.
Thanks, Professor O'Brien. I'm going to ask one quick question. If each of the panelists could give me your 1 minute take on this, 1 minute or less. So let's say this time is different in terms of where like hydrogen is. This is not a new hype. This is now the time for hydrogen. From your perspective, from the research angle, why? We can start with Professor Fowler, maybe.
I can do that. First one, just what the reason hydrogen is more important is that certainly all the EU, everybody who's done the renewables, they have realized that solar just won't get there. Wind will not just get there. They need energy storage to support those renewables. And in order to have those long-term energy storage, hydrogen is the way that it can allow to enable renewables. Also, I can also let you know is that people know is that eventually we're going to have to do nuclear too. If we want to keep running in vehicles, 10 years by, we're going to need more hydrogen. We're going to need more electricity, and we're going to be CO2 free. If you look at what's happening in Germany, as they built all the wind you need, it was built in Germany. But then they found out that they didn't have the hydrogen to provide the energy storage. So their electricity's gone up to about 28 cents a kilowatt. France, right beside it, is down half the price at about 15 cents a kilowatt because they have nuclear and they're going able to do the management for it long term.
Thank you very much, Professor Fowler. Professor Wu, would you like to go next?
Yeah, so I would like to comment that in the point of academia. So I think hydrogen economic is a very complex problem, ranging from different fields, different sectors. But I think this time we are more prepared because the professors, the students are dealing with this multidisciplinary researches for a long time. So in this case, we are more prepared to connecting different sectors into one subject and then solve this problem with all our expertise. Thank you.
Thank you very much. Professor Fraser, would you like to go next?
Sure. Just I'll just reiterate a bit of what Professor Fowler said. I mean, it boils down to, if you're going to have renewable energies, you've got to have a storage medium. There are options. Like I said, I do compressed air as a possible storage medium. You can use pumped hydro at large scale to storage medium. But really, chemical energy, if you're going to have something that's distributed and locally available without a large infrastructure, but you can move it, there is an infrastructure, but you can move it around, you need some form of chemical energy. Hydrogen is a form of chemical energy at a fair concentration, but of course it's not as concentrated as gasoline. You have the compression difficulties. Hydrogen can also be incorporated into, say, methanol production. And so you can carry it through a chemical bound methods. As I mentioned, there's different ways to store hydrogen at the beginning of my presentation, chemical method, hydrogen method. But to me, the big stumbling block, it's the same with wind and solar. It's the storage aspect. You don't have storage, you'll never get the high demand. Once you have storage, opportunities are going to open up, economies of scale are going to advance, and it's going to become economic, much more economical. And the health and clean benefits of it, people will appreciate it. I'll just make a quick note. Historically, we have always moved locally from dirty fuels to cleaner fuels. We used to burn coal in our home. That was dirty. We then burned, well, first it was wood. That's the worst. And then we had coal, and then we had oil. Now we have natural gas. Some are going to electrical, but it's not quite as efficient. The next thing would be hydrogen. There's a progress here of the fuels and energy sources we use close to us that affect our health of being cleaner and cleaner, and it will happen. We will move to hydrogen.
Thank you very much. And Professor O'Brien.
Yeah, thank you. I know we're running short on time, so I'll try to keep it quick. I liked what Professor Fraser had just said there, and it's true, we do continuously move towards cleaner fuels, and there are a ton of challenges in taking the next step to hydrogen. But it's the thing that's different now is people realize that there's a sense of urgency due to climate change and global warming and other environmental factors. And now globally, we're seeing divestments in fossil fuels, and due to public pressures and ultimately working its way up onto policymakers and so on, people are realizing it's time to invest in this next step to a cleaner fuel such as hydrogen, and it is needed due to the energy density and chemical fuels, which we will depend on. That's it.
Well, thank you very much. We're 1 minute over. I guess some of my learnings from this last minutes from you is, well, why is this time different? Well, the tech is ready, the public is ready, and the pressure is on. So, you know, great job, everyone. We need all the research we can get and all the technology we can get. I just wanted to say we're going into the break now. I know that some of you would be working in will be presenting in another panel too. So if that is the case, I think Professor Fowler, do jump into your prep session coming up at 10:30 or 10:32. And then I guess we'll see everyone after the break. Thank you very much. And thank you very much to the attendees. This was a very well attended panel. Thank you very much.
Thank you.
Thank you.
Thank you, everybody.